Hello everybody, this is Doug, and in this video we're going to talk about amines, and this will be the first part of our introduction. And this one we're just going to kind of cover what they are, the types of amines that there are, and then some of their physical properties. And to make sure that we're all on the same page here, right, amines are just when you have a nitrogen, and that nitrogen is attached to either hydrogens or carbon groups. I'll put R here. But these carbon groups have to be sp3 hybridized, right? Not sp2 or sp. If they're sp2, you might actually be talking about an enamine or an amide or an imide or something else. So it could have 3 R groups on there or 3 hydrogens on there, but that's what would make it an amine. It's not something that is double bonded to something. That would be like an imine or something like that. So we're just talking about things that have sp3 carbons attached to them. Here's a ton of different amines, right? They're really, really an important functional group. You see them all over the place. So, I mean, like, we find them in here's one of my favorite names for a molecule. It's putrescine. And as you might guess, it smells terrible. But you'll notice, right, that it's got 2 amines on it, right? It's got an NH2, and then it's got that carbon linker between the two amines. So putrescine is super smelly. There's spermidine, which is a very, very, very common. It's in most living organisms, but it's a very common biomolecule. Very common biomolecule. Really important for a lot of cellular functions relating to potassium and calcium and even ATPase, I think. It's supposed to be a good supplement. You find it in a lot of foods. It's supposed to be good for your heart, your hair, longevity, all kinds of things. Spermidine got its name because it was actually found in semen first, but scientists later realized that it's found in like every cell, all kinds of, it's in plants, animals, everything. Threonine is just an example of an amino acid. Right? All amino acids have amines in them. That's why they're called amino acids, which is something that hopefully we'll talk about later. Here we have choline, which is another very important biomolecule. Choline, you may have heard of like acetylcholine is a neurotransmitter. Choline can be found in, well, I'll put that neurotransmitters. Find that sucker in neurotransmitters. It's in a lot of phospholipids. Not all, but a lot of phospholipids have choline in them as their polar R group. But you notice in all of these here, right, the idea is that what we have is we have these nitrogens that are sp3 hybridized and that have carbons and hydrogens only attached to them, right? Whether it's in threonine and even in choline, right? This one has 4 groups on it, and we'll talk more about that in a second. That'd be a quaternary nitrogen, but it still would be considered an amine, still in the same group. You can also find amines, right, in adenosine. You may have heard of adenosine, especially if you've taken any biology whatsoever. Adenosine is, it's everywhere, right? It's in your RNA and DNA. Write that down. Right, you find adenosine in your RNA and DNA. It's a backbone of ATP, which is adenosine triphosphate. It's part of things like coenzyme A. It's everywhere. It's in all over. It's all over. It's in important coenzymes like NAD plus, which is nicotinamide adenosine diphosphate. I mean, it's everywhere. It's all over the place. Super important biomolecule, but again, you notice that it has an amine in it. Whoops, which is right up here. Now, those other nitrogens in those rings, we can talk more about later. They have a lot of the properties of amines, but technically, we've got like a pyrimidine in there and an indole, and we have different functional groups in there. They're still going to be basic and relatively nucleophilic to a degree, but I'm just highlighting the NH2 right now because that's the most normal, straightforward amine, and that's the type of amine we're talking about right now. We've all heard of morphine, right? Morphine is one of those opioids. You've all heard about that opioid epidemic, right? We have a tertiary amine in that one, right? We've got a nitrogen there. So all of your like codone, oxycodone, all of those sorts of things, hydrocodone, those are all very closely related to this morphine here. I think I said codeine and even heroin, right? It has the same sort of background, but it's got an amine in it. as does dopamine, hence the name, and methamphetamine and amphetamine, right? They all have the word amine in them. Dopamine, right, is a super important neurotransmitter, makes us feel good, one of the feel good neurotransmitters. It's not the only thing it does, but still. Let me give myself some more room here. Right, so dopamine's an important neurotransmitter, which is why some drugs like methamphetamine, right? So we have amphetamine, which is down here. I should have switched these maybe. Amphetamine right here is, I mean, Adderall is for ADD or something, ADHD, right? Adderall, some people might take it to help focus. But amphetamine, right, again, is a neurotransmitter. You notice that they have the same sort of background. This is not a neurotransmitter discussion, but I'll just point out that you have the aromatic ring, 2 carbons and a nitrogen. Aromatic ring, 2 carbons and a nitrogen. Aromatic ring, 2 carbons and a nitrogen is a common backbone for some of the neurotransmitters and some drugs that people make to mimic those neurotransmitters. So, like you've probably all heard of methamphetamine, right? That's meth. When people talk about meth, you've watched Breaking Bad or something like that. It's exactly like amphetamine. It's exactly like Adderall, except it has an extra methyl group on there, hence the term methamphetamine. But all of these are amines, right? They're all over the place. This is nowhere near all of the examples. They're all over the place, which is why we're going to spend so much time talking about some of their properties and then how to make them. Like, how would I make any of these molecules? Now, we want to talk about the types of amines that there are, right? So ammonia, probably you've heard of ammonia. Think like window cleaner, something like that, but that's just good old NH3. And then we do have primary, secondary, tertiary, and quaternary amines also. And that just refers to how many carbon groups are attached to that nitrogen. So for example, with putrescine, if I look at this amine here on the left, it's only got 1 carbon group attached to it. So that would be a primary amine. This nitrogen on the right-hand side only has 1 carbon group attached to it, so it's also a primary amine. Right? They just have 1 carbon group attached. It's not like alkyl halides or alcohols where you're talking about how many groups are on the carbon that the OH is on, or how many groups are on the carbon that like a bromine is on. This is actually how many carbons are coming off of that nitrogen. How many of its groups, how many of the groups of it are carbon groups. So again, if I look at spermidine over here on the left, this nitrogen would also be primary, but the one in the middle, right, has 2 carbon groups coming off of it, so that would be a secondary amine. And then over on the right-hand side, we have another primary amine. Threonine also has a primary amine here, right, 1 carbon. Now choline, right, has 1, 2, 3, 4 groups coming off of it, so that would be a quaternary amine. So we do have quaternary amines, and they are important biologically. There are things like choline, for example. I should also mention, let me just draw this here. Since this is COVID time that we're talking about, you may have heard of quat disinfectants. Quat disinfectants, like an example of one would be the benzalkonium things, where they have some sort of long chain. Who knows how long? I mean, the chain can vary in length, and then often 2 methyls. And so this would be an example of a molecule that acts as a disinfectant in something like, Lysol or Clorox disinfecting wipes, stuff like that. And these are called quats. These are called quat disinfectants. And they're called quats because, right, this nitrogen here is quaternary. And it has some counter ion like chloride or something like that. But the idea is that these are kind of soap-ish, and they help to disrupt that phospholipid bilayer because they have these long fatty tails, kind of like you would see in a phospholipid. And so they can disrupt that bilayer and then kill the virus or bacteria or whatever. But so we do have quaternary amines. They are relatively stable, so you see those around. So here's a bunch of primaries, secondaries, quaternaries. I will just do the one on top. You're right, this would be a primary amine up here. You can talk about whether they're primary, secondary, tertiary. These amines down here, we would call all of these all behave like they're tertiary because they don't have any hydrogens on them. And they all have 3 bonds to carbon. Even though there's not literally 3 carbons, we still treat them like they're tertiary in terms of their basicity often correlates, although these are on rings and aromatic. These have delocalization that we need to talk about. But and so, as far as the types of reactions they can do, right, they behave like tertiary reactions, right? Like they can't form amines and enamines, even though they're only attached to 2 carbons. For morphine, here's our first example of a tertiary carbon, right? Because this nitrogen right here is attached to 1, 2, 3 carbons. So you have tertiary amines and all of those opioids I was talking about, whether it's heroin or oxycodone. And primary amine in your dopamine, secondary amine in your meth, and primary amine in your Adderall, right? So again, you just look at how many carbons are attached to those carbons. And this will be important. I'm going to show you a slide later where we're going to learn a bunch of different reactions to make different types of amines, right? So we'll learn, for example, that like something called the Gabriel synthesis. It only makes primary amines. We'll look at something like a reductive amination, which can make primary, secondary, or tertiary amines. And so we'll want to be able to look at these amines and be like, oh, that's a tertiary, so I know I can't do a Hoffman rearrangement, and I can't do a Gabriel synthesis or something like that. So it's going to kind of help you organize what types of reactions we can do. So some of their physical properties here, generally speaking, right, they have amines have lower boiling points and melting points than alcohols, but they're higher than just a regular hydrocarbon. And that's because they have weaker bonds, right? So if you take a look at these molecules here, they all have roughly the same molecular weight. Their molecular mass, but they have very different boiling points, right? Butane's about 0, and then you have your propylamine is about 50, and your propyl alcohol is closer to 100, right? So that's a jump of basically 50 degrees centigrade from one to another. Oh, sorry, these are all their boiling points, BPs. Now, if you look at your amine versus your alcohol, right? So the difference here, what I mean by the weaker hydrogen bonds is if you take a look at your H-N bond versus your H-O bond, and you look at the electronegativities, right? Hydrogen's sitting around 2.2. Right, so both of these hydrogens are about 2.2 for their electronegativity. And the nitrogen's sitting at about 3, whereas oxygen's sitting at about 3.4. So if you just look at these two, right, in terms of their electronegativity, the amine has a smaller difference in electronegativity, right? The electronegativity of nitrogen and hydrogen are closer together, whereas OH has a larger difference in electronegativity, so that translates to larger charges, right? Smaller difference in electronegativity, smaller charges, right? And we know this. That's why things are nonpolar if they are really similar in electronegativity. You have basically no charge, and if you have really big differences in electronegativity, you go basically ionic, right? So you have like a full-on charge. So if I was to assign partial charges for this, and I'm going to do this just kind of real qualitatively, I'm going to put a big old delta minus on that O, a big old delta plus on that H, a big old delta plus on that carbon, and I'm just going to put a smaller ones on those on the amine, right? They're just going to be a little bit smaller. They're still there. They still have dipole. It's still hydrogen bonding. It's just smaller charges, smaller attraction, right? So these just have less attraction. And that's the idea, which is why it has a lower boiling point. It's easier to break up. Also, smaller amines are water soluble, right? They can hydrogen bond, right? They can hydrogen bond with water. Right, so if you have two amines like this, what we're saying here is that this amine, and maybe I should draw this out a little bit more. Got partial positive, partial negative, partial positive, and positive. And if I had a water molecule, right, imagine this being surrounded, right, by water molecules. That we can have, I'm just drawing dotted lines here to indicate that attraction here, right? You can have a hydrogen bond. Again, it's not as good as if it was with another OH or an HF, but it is a hydrogen bond and there is attraction. And so small-ish amines, so like less than 8 carbons roughly, give or take as a rule of thumb, those tend to be water soluble. If they get too much longer than that, get too much bigger, if you have like 10 just hydrocarbons attached to one amine, probably not going to be very water soluble. And so I would say a smaller one like this is water soluble, whereas the larger one on the right hand is not. Right, because the one on the left has 1, 2, 3, 4, 5 carbons. This is a 5-carbon chain, and this is a 1, 2, 3, 4, 5, 6, 7, 8, 9. 9-carbon chain, too much. That's not soluble. That's not going to be very miscible with water. Now, well, I might as well say this now, although we'll talk about it a little bit more in the next video. Amines are weak bases, and so what you can see is that if an amine is in a slightly acidic condition, a slightly acidic solution, it can get protonated, which means it's now going to bear a charge, and that will be more soluble. So I'll just put as a side note here, protonated amines are more water soluble, right? It has an ion now, so it's even more attracted to water. It's going to become more soluble in that polar solvent. So protonated amines are more water soluble. And this is often a way, you may have done this in a lab before, but this is often a way that we isolate amines, moving between the organic and the aqueous layer, is by playing with their sensitivity to pH, right? If you protonate an amine, it's going to move into the water layer. If you deprotonate an amine, oftentimes it's going to go more into your organic layer. So it's something that you can play with if you're trying to isolate them. So we're going to talk more about the acidity of amines, the basicity of the amines, and the nucleophilicity of amines in part 2 of this introduction. So I hope that you don't have any questions with this. This is just some good background information about amines, what they are, how we classify them.